Howdy YouTube, Esnix here with another video for you. We're back in Arch Labs. Yes, this is really becoming one of my favorite places to be. Debian's really nice, very comfortable, very easy, never gives me a problem. Arch Labs is slowly approaching that. I haven't used it nearly as long as I've used Debian-based systems. But for Arch, it's really pleasant. And that's saying a lot for me because my experience with Arch-based systems is more miss than hit. So, Arch Labs, you're doing good. Let's continue the good luck here. We're going to start off an update here because there's stuff to get. Yet again, I just did this 2 days ago, and there's already new LTS kernels, new current kernels, a whole lot of stuff, new Chromium. You know what? Let's close Chromium, and let's just start the update here. Now it wants my password. And away it goes. Very good. Hopefully this won't take too long. Looks like it's moving along quite well. So we'll minimize that. And what I really want to talk about are permissions. Now, I guess every Linux user, Unix user, once they get a handle on permissions, they feel so, well, you've learned something. And for years, I never really concerned myself with file permissions. I just let the system handle whatever it handled the way it handled it, and only had to think about them if there was a problem, which there rarely ever is. But the last video I did with Arch Labs, we came across a file conflict in an upgrade, in an update. And the solution to the file conflict was renaming the old file because it didn't have a package owner. It wasn't owned by a package. And that, when I renamed the file, the permissions had been changed from 740 to 755, and that was not. So it got me thinking about file permissions. It really wasn't a big deal. I wound up deleting the file anyway, so it wasn't a problem. However, as I said, it got me thinking about permissions. Now, I wrote up a little document that I'm going to go over. And in preparation, I set up a temporary folder, created a whole bunch of files and a couple directories. And we're going to get into that folder here. It's just called perms. And there we are. We're in perms. And if we do an ls, well, it already did the ls. If we do an ls, we don't really see a whole lot of information about the files and the folders. We can see the folders are blue. There are some files that are green, most are white. Now the green files are executables, the blue are folders, of course, directories, and the white are just files. In order to see some more detail about what we're looking at, we can use ls with the L switch, and that gives us a whole bunch of columns now. And in that first column, you see a whole bunch of letters. Now the two directories, the letter strings begin with the letter D, the files begin with a dash, and that's right here. D for directory, and dash, this first character here is a special bit that we really don't have to concern ourselves with for the purpose of my little chat here. We're really concerning ourselves with this string. Ah, good. Package manager successfully updated. System up to date. Cool. We can reboot later. Okay. Back to the directory here and the files. We see strings of letters and dashes. These represent the permissions of the file or directory. And they're divided into 3 sections. There are 3 sections of 3. We have 3 bits, another 3 bits, and a third 3 bits. So a triad of trinities, right? Or a trinity of triads. Now, the first set of 3 bits refers to the permissions for the owner of the file. Now, in Unix and Linux, every file has an owner. Every user is a member of a group. The second 3 bits here represent the group permissions. The third 3 bits represent the rest of the world, or any other user on the system. So let's minimize this and take a look at the document I've been building up just for this purpose. Now hopefully you'll be able to see it. And what I'll do is, this information is out there. It's been covered, I don't know, a ridiculous number of times. But what I found in my own learning is that it took one particular explanation for me to finally get it, and get it in a way that now I don't think I'll ever lose it. It's sort of like riding a bike. Once you get something, you just get it. And then it's easy, right? Right. Okay, file permissions. The trinity is the owner, the group, and all others, represented by 3 bits each. Okay, dashes. Symbolic, there are different representations for the permissions of a file. There is read, there is write, and there is execute. So the full permissions of a file will specify the read, write, execute for all 3 types of users. The owner of the file, the group that the owner is in, and all others. The RWX is referred to as the symbolic view. Now in English, it's read, write, and execute. Now, each bit, I'll refer to these as bits because they're binary bits of information. In each of these slots can be a 1 or a 0. That's binary. You can also refer to the combination of these 3 bits as an octal number. And converting between binary and octal is pretty simple. You just should bring up a calculator. I just used an online one. Typed into Google binary to octal conversion, and you get a nice calculator. You type in the binary, or if you want the decimal number, if you want to use decimal. But no one uses decimal for this, so why am I doing that? So the 3 bits can be shown as symbolic, RWX. They can be shown as binary bits, 1s or 0s, or all three can be referenced with one octal number. So, in the case of file number 2, we see the permissions are right here. So we have the owner, RW dash. In English, the owner can read and write this file. In binary, there's a 1 in the read column, a 1 in the write column, and a 0 in the execute column. So therefore the binary is 110. In octal, that binary converts to the octal number 6. The group has the same permissions as the owner: read, write, not execute. In English, read, write. In binary, 110. And in octal, 6. Others have the same permissions. Now, 666 is not a devilish number. In Unix, it is the standard for files. All files are created equal. There's a pun there somewhere, right? So the beginning permissions for every file is assumed 666. Read, write, owner, group, and others. If you notice, if you create files, they actually don't get 666. They get a slightly different permission set. They actually get 644. Now, this is a little stricter, and it limits other users' ability to change or delete your files. You, as the owner, can read and write. You have 110 binary permissions, 6 octal. However, the group and others can only see or read the file. They can't write or change or delete, and they can't execute. So their permissions are 100 in binary or 4 in octal. So the way we'd specify the octal permissions for this file, file 1, would be 644. That's the quickest way to reference the permissions of a file or directory, is with the octal notation. Once you get a grip on the fact that the 3 sets of 3 bits represent a binary triad, it's pretty easy to convert binary to octal. Once you know the octal numbers, it's very easy to then go and change permissions and specify. The first column in the permissions bit, well, every column in the permissions bit can go from 0 to 7. Octal being a base 8 number system, you have digits 0 through 7. That is why you will never see an octal number higher than 7. 7 would be a 1 in all 3 columns. Now, you might ask why, when you create or change files, the files you change or create get the octal notation of 644. Many Linux distributions use a standard rule called a umask. This rule is applied to all files and folders created by users. The most commonly used umask is 022. Now, 022, what a umask is a rule that specifies with octal notation permissions to be taken away from the default file permissions of 666. So when you're dealing with a file, the standard permissions are 666. A umask of 022 will leave the first column alone, 0, no change. The second column will be diminished by 2. The third column will be diminished by 2. Now it's not so much subtracting as it is taking away well, it is subtracting, I guess. From 6, you're getting to 4. In octal notation, 4 would be represented by 100. 100 in binary is the same as 4 in octal, which is a 1 bit in the first column, or the third column, depending on which direction you're looking at it. The highest order column. If you convert binary to octal, you will get 4. That's just what it is. So that's what the umask does. Now, system-wide, the umask is specified in a little file in etc. At least in Arch, or this, and I believe in most Linuxes, in a little file called profile. And you can see it right up here at the top of the file. Set our umask 22022. If you wanted to change the umask of your user, which I don't recommend you doing because it will have strange consequences down the road, you can go into your own home folder, find your profile, and in my folder it's X profile, and add a line, umask 002 if I want, and that will set the umask for my login differently from the system. Now, I'm not going to do that, but you can if you really wanted to. Just want to show you how to do it. Okay, folders. Well, okay, before we get to folders, let's get to executable files or programs. Now, if you write scripts or you just want to know what the permissions are on executable files, the execute bit is the third bit in each of the groups of 3. So a common permission set for programs, binaries, executables, at least in Arch Labs and probably in Arch in general, where your user is a member of the group users, a very safe executable file permission strategy would be represented by the octal notation 744. 744 would allow the owner of the file read, write, and execute. The group just read, and others just read. Now, most executables are going to be owned by root, or be able to run because their other bit may be set to execute, allow others to execute. So in this case, this particular file would be executable only by the owner and no one else. On systems such as Debian, where the owner is a member of the group of the same name as the owner, this is true on Debian, on Ubuntu, and derivatives of those systems, probably others, you might need to set the executable bit for the group as well as the owner, but not for others. So it'd be slightly different. The file permissions on a binary or executable would be 754, allowing execute and read for the group and only read for others. Hopefully I'm not confusing the issue too much here. The biggest thing to note is that on executable files, the execute bit will be set, so the octal permissions will start at 7 instead of 6 for non-executable files. Now we get to folders. Now folders are slightly different than files in that the execute bit on a folder has to be set for people to be able to, for users to be able to open the folder and look inside. So the default permissions on folders in Unix and Linux is full 777, read, write, execute. I got this wrong, didn't I? Read, write, execute. See, I gotta edit my own work. Okay, there we go. That's more like it. So the default folder permissions in Unix and Linux is read, write, execute across the board. The umask that affects files also affects folders. So when a user creates a folder, the umask changes the permissions from 777 typically to 755, stripping away the write ability from group and others. And you are left with 111 for the owner, 101 and 101 for group and others, or read and execute. So when you look at the string of symbolic representation here, once you get how it works, that they're binary bits represented by letters and can be converted into octal notation from binary very quickly, you can look at this and say, okay, RWX 7, R-X 5, R-X 5. That would be 755. If it were, say, RWX R-R-, it would be 744. It's pretty much how it works. Now, this is a way, say you wanted to hide the contents of a folder from all other users on the system except for root. Now, if you're the only one that can access root, this will work. If someone else can access root, it doesn't really work because root can do anything. You can change the permissions on a folder to 700. This will allow you, the owner of the folder, to read, write, and execute. Anyone in your group or all other users have no access. 0 bits, 000 binary, 0 octal, nothing. They can't do anything. They can't even see inside the folder. So, if you'd like to hide things from others, you can try using Unix permissions on folders to do that. The folder won't be invisible. You can make it invisible by putting a dot in front of it. So, there are ways to hide files and folders. Now, how do we view the permissions? I think we just covered that at the beginning with the ls-l. How do we change permissions on a file or folder? Well, here comes the chmod command. Stands for change mode. I thought it was change modality, which is pretty much the same thing, but change mode is easier to say. So we'll stick with that. So if on a file, say file 1, which is set to 644, RW dash would be 6, R dash dash 4, R dash dash 4. So if we wanted to change the mode on file 1, we use chmod, specify the new mode for the file, 655 say, and file 1. Now if we ls, you can see what we've done. File 1, we've made, it's a pretty useless change, we've made it executable for group and others, not for the owner. Group and others still can't write to it, but they can run it. The owner can read and write it, but not run it. So 655 was a strange one to pick. I don't know why I picked that. Just popped in my head. Now, we can change it right back. Now, instead of typing ls space dash l, a common alias for that command is simply ll. Now, this is aliased in Arch Labs. It's aliased the same in Debian. It's probably a very common Unix alias to do that. Very quick way of getting ll. And you can see we changed file 1 right back to 644. Now files 4 and 5 you notice are green because they're executable. And I believe that's what the little star stands for as well. But I'm not sure. Star might be, no, it's not modified because we just modified file 1. Probably just executable. The green color and the star asterisk. So there you go. There's a breakdown of permissions on files and folders in Linux. I hope this clears something up for someone. And Our system is now up to date. Cool. We are up to date. So I will end the video and reboot and see you in another one. Bye-bye, folks.